Alright, so what we've learned so far is that if you take the derivative of a function, it's going to give you a gradient. And if you have a gradient function, let's say f dash of x, so over here I have f dash and I sub in a value of, well, some constant a instead in place of x is equal to 0. This must mean that there's a stationary point at x is equal to a. So when I mean stationary point, something like could look like, wait, where's my pencil? Here it is. Okay, looks something like this. So this is a stationary point because your gradient is completely flat. So we call this, well, I'm just going to call it SP for now. I'm not going to write out a 4-syllable word every time. Wait, 1, 2, 3, 4. Yeah, 4-syllable word every time. It's quite long, so I'm just going to call it SP in this video over here. Now, the point is that it's not always going to be a stationary point of this nature, because, I mean, this is what we call a maximum, right? And there are other kinds of stationary points. So let's just list the ones that we do know so far. So what we just said over here was the maximum stationary point. So this is the one where you want to curve up, come back down, and the stationary point is around here. Okay. What other ones are there? Well, I mean, if there's a maximum, then just corresponding, there should be a minimum, right? Exact opposite. Now, minimum, as you may have seen in parabolas or whatnot, is something like when you come from the top, curve down, turn right at the bottom here, and you're going to have a minimum, or we can say minimum turning point, right over here. So these are two possibilities of stationary points. Do we know any more? Well, I'm sure you've come across what we call a stationary point of inflection as well. So, of course, it's sport. Okay. And just so we're not confused with poi as a point of intersection, this I over here means inflection. And of course, the S and P means stationary point. And when you have a stationary point of inflection, then there's two possibilities over here, and they're both stationary points of inflection. But the idea is that you either come up completely flat, go back up, and your stationary point of inflection is right where it's instantaneously stationary, of course, or you're going to have a horizontally flat gradient. And of course, if you want to have the other kind of stationary point of inflection, then you can come from the top, make it flat, go back down. This is also a stationary point of inflection. And the reason why I'm showing you all of these possibilities is because we can actually describe the nature of each of these stationary points, not just by inspection of its visual features over here, but you can tell what kind of gradient it is, what kind of stationary point it is, by observing the gradient on either side of the stationary point. So if I just scroll down here, for example, in your maximum over here, we can see that going from the left to the right, what do we have on the left over here? Well, the gradient is continuously going up as we go from left to right. And when it continuously goes up from left to right, we say that the gradient is positive over here. And right as we have our stationary point, our gradient is 0 here. And then if we're going from left to right and we're going down continuously, our gradient is negative. So just to clarify over here, what I'm going to do is I'm just going to make a list of how the gradient changes throughout. So over here, I'm just going to describe the gradient for all of these different stationary points. Okay, and for the minimum here, let's observe. We're going down, so we have a negative gradient here. So it starts off as a very steep negative gradient, and then it just slows, well, not slows down, it flattens out until it's stationary. So we have a negative, it's going to be at 0 now, and then it turns back into a positive gradient. And that's another reason why we call it turning point, because it turns from negative or to 0 and then positive again. Now for SPOI, what do we have here? We have a positive gradient. Positive gradient becomes smaller and smaller until it hits 0. So we're going to say positive hits 0. What happens after the stationary point though? Well, it actually goes from a small positive gradient and turns very big again. So in fact, it goes from positive to 0 and then positive again. And if you were to look at these 4 possible stationary points over here, you may realize that the last combination is that you're going to have a negative gradient to start off with, 0, and then after the stationary point, it's going to be negative again. And to describe all of this, we can actually just use a few symbols over here. The symbol of the slope. And what we commonly use when we describe the nature of these points is we say that when it's a positive gradient, we just draw a straight diagonal line with a positive gradient. When 0, we draw a flat and horizontal line. And when it's negative, we draw a diagonal line like so. For the minimum, then we have a negative gradient, negative, flat, positive. For the stationary point, we have positive, flat, positive again, and of course over here for negative, negative gradient, flat, and negative again. And this is the kind of notation that we're going to be using when we describe each of these. So whenever you want to test out the nature of a stationary point, you want to just observe or find the gradient of some sort of point on the left and right of your stationary point. We'll go through a few examples with some actual numbers rather than just describing it like this. So over here, we have a cubic function, and we want to find the stationary points and justify their nature. Now, you can use your CAS and just simply graph it out, but that's no fun all the time, right? And while using your graph page, you don't always get the number of sig figs that you want. So there's going to be a few CAS calculations here. So if we run into any weird numbers and big exact values, you're going to need your CAS for this. Otherwise, I'm just going to jot down the numbers that I got from my notes. So the procedure for finding stationary points is, of course, you want to find out when your gradient is 0. So what defines your gradient? Well, your gradient is f dash, right? F dash over here, the derivative of a polynomial is quite simple. X cubed turns into 3x squared. Minus 4x squared is minus 8x. And over here, minus 3x becomes minus 3. And we want to set this equal to 0 for our stationary point, or any stationary points that we can find. Solving for x over here will give us the x coordinates of any stationary point. So if you do solve for this, then over here, x will equal to, well, you can just factorize over here. It is a quadratic. You're going to get either negative 1/3 or 3. Okay, so of course these are just x coordinates of your stationary point. If you want to find out what the coordinates actually are, then you need to sub these back in. So that means we need to find out what f of negative 1/3 is. It's going to be 500 on 27. So I use the CAS for this, of course. I mean, you're welcome to think that I did that in my head, but nah, don't believe that. It's nonsense. F of 3, when x is equal to 3, you're going to get 0 over here. Okay, whoops. And of course, this implies that you have two coordinates here. You have SP at either negative 1/3, comma 3, and 3, 0. Now we want to know what kind of stationary points these are. So what we're going to do is we're going to draw what we call a nature table. So over here, what color should I use? Maybe blue, not sure. In any case, in the nature table, you're going to have 3 rows. You have x, f of x, and your slope. Okay. Alright. And over here, when x is equal to -1/3, we know the gradient is 0. When x is equal to 3, we know the gradient is 0 again. Okay, so that's what we know so far. And of course, you can actually just say that the slope looks like a flat horizontal line. So we're just trying to imagine what the tangent will look like. Now over here, the reason why I left space on the left and right of both of these x values is because, remember, we want to find out what kind of gradient you have on either side of these stationary points. Like up here, for example, for maximum turning point or maximum stationary point. On the left side of your stationary point, the gradient should be positive. On the right side of your stationary point, it should be negative. So we're going to test out what's on the left and right. Okay, so over here, we're going to test out, well, it's probably nice to use some familiar values, or not familiar values, some whole number values, which just help you out a little bit, especially if you're subbing in tech free. So in this case over here, what we can do is we can use 0. It's right in between the two. 0 is generally a good number to sub in. Less than -1/3, but still a whole number. We make it -1. And on the right of 3, we can use maybe 4. So just increase it by increments of 1. Okay. So if you want to find out what the gradient when x is equal to -1, then we simply need to sub in. Okay, so maybe I'll just do it on the side. Where's red? Red is over here. Okay, so we need to sub in f dash of -1 when x is equal to -1. Just doing this on the CAS, so we're just subbing it into this over here, 3x squared minus 8x minus 3. This will give us a value of 8. Now if you record this value onto your table, then you can draw the corresponding slope. And since 8 is a positive number, you know that the slope is going to be positive. So just draw a positive gradient like so. You don't have to draw how steep it is. It doesn't have to be specific like this or like this, or even like a flat gradient like this. Just any positive looking gradient is fine, because we just want to know the nature, not actually sketching a graph. Over here, when f of x is equal to 0, so if you were to do the calculation on your CAS, just sub in 0 for your f dash. This will give you -3. Okay, let's just finish with x equals to 4 as well, just while we're at it. So 4 into f dash, and this is going to give you, what's it going to give us? Actually, I don't have this on me at the moment. So we're going to get 3 times, what did this in, what color do I have? Yellow. Okay. Get 3 times 16, so we get 48, minus 32, minus 3. So this is going to be giving us 16 minus 3, which is 13. It's a positive number. Okay, and from here, we'll just draw the slopes corresponding to the value of f dash. Now f dash here is negative, so let's draw a negative slope. Slope with a negative gradient. F dash here is 13, is positive, so we can draw a positive slope. You can see over here, you can kind of visualize a cubic over here. So if I was to continue drawing what this looks like, then if I just draw in green over here, maybe, the slope will look something like this, as expected of a cubic. And what this tells us over here is that for the first 3 parts of this table, you have a maximum, because for a maximum, you go up, it's flat, you go back down. So this means that 0 over here, since it's a positive on the left and negative on the right, 0 is a maximum. So that's what we're going to write down over here. Let's see. This one is a maximum. And over here, this 0 comes from the top, is flat, and then goes back up. So if there's a negative on the left and a positive on the right, it's a minimum. So you can kind of see how this is like a positive parabola, whereas x equals to 3 is at the very center. So this one over here is a minimum stationary point. Right, just to try out another example over here. Now we're presented with a quartic. We want to find the stationary point. So very similar procedure. So first of all, what we're going to do is just find out what f dash is. F dash of x, derivative of negative x to the power 4, negative 4x cubed, derivative of negative x cubed minus 3x squared. Next one is 6x plus 5. Okay, and we want to equate all this to 0 for our stationary points. Okay, so if you do solve for this with CAS or whatnot, it's kind of hard to do cubics by hand. Well, I wouldn't say hard, but it's very time consuming. Then you should end up with two values of x. So x is equal to either -1 or x equals to 514. Now, of course, you can use your factorization on your CAS if you want to just see what the nature of these are, especially if the x-intercepts, but that's only if the x-intercepts. And so this is where the nature test comes in handy. So over here, if we begin our nature test, maybe we'll find the coordinates afterwards. You can really do either one first. The order is really interchangeable. So nature test means that we need 3 rows, x, f dash of x, and our slope. Okay, and what we're given so far is when x is equal to -1, f dash is 0, your gradient is 0, f dash is 514, our gradient is 0, and our slope is going to be completely flat horizontally. Now over here, we want to sub in some values of x on either side of both of these stationary points. So on the left of -1, you can have -2. On the right, maybe 0. This also acts as the left side of 514. So we just need the right side of 514. This is approximately, it's a bit more than 1. So let's go with something like 2. Okay. And from here, we just need to sub in f dash of -2. This will give us about 13. F dash of 0 will give us 5. And f dash of 2 will give us -27. Okay. And from here, try drawing our slopes. So the first one over here is positive. This one here is positive as well. I'm going -1 here. So again, if you want to draw, just sketch the graph really quickly without any axes, you can if you want, just to give yourself a better idea. But this quartic will look something like this. So it needs to go up, be flat, go up again, be flat, and then comes back down. Okay. So the regions where it's flat should be over here and over here. Alright. Now, what does this tell us? Well, it looks like over here we have a spot. we have a stationary point of inflection. Since we know for a SPOI, the gradient doesn't change sign before and after the stationary point. So over here, it's positive first, and it's positive again. So it must be a stationary point of inflection. Of course, if it's negative, negative, that's also a stationary point of inflection. Over here, it's positive, flat, and then negative. When this happens, you can kind of see that this is going to be a maximum turning point. And so now all we need to do is find the coordinates of when x is equal to -1, x is equal to 5 on 4. So simple procedure there. All we need to do is just sub it back into our original rule. So we got f of -1 equal to, what is it, 0? And f of 5 on 4, which is 2,187 on 256. And so two coordinates here, -1, 0 is a SPOI, stationary point of inflection, and 5 on 4, comma, this big fraction over here is going to be a maximum stationary point.